This is May, June 2025, paper 42. These are the grade thresholds. If you want to score these respective grades, this is what you need to cross in order to be able to get that grade. The first definition is define the radian. This is very simple. We can copy the answers from the marking scheme. Part B. The rear wheel is given the situation, so on and so forth. It passes around the cogs. It looks like a bicycle system. There is a small cog and there is a larger cog for this. Rear wheel radius is mentioned and large wheel radius is also mentioned. Let's move on to the question. So he says all the data is given to you and is fixed to the pedal so that it rotates with them, just like a bicycle system. Says the bicycle is being pedaled so that it moves straight in a straight line at a constant speed of 17 meters per second. Calculate the angular speed. So the formula that we most likely are going to use is V equals to R omega. Now the idea behind this would be, what should be the value of V? Because we want to find omega, what should be V? Since we are interested in the rear wheel, the radius will be 0.038. That's a no-brainer. Sorry, not the cog, it's the radius of the wheel, yeah, 0.46. So this is 0.46 multiplied by omega. But what should be the velocity V? You see, when he says it's moving in a straight line, that means that for this larger wheel, the tangential velocity V is actually 17. So based on that idea, it should be 17. This is omega equals to 36.9 radians per second, which becomes 37 up to two significant figures. Then we have next question as part 2. Calculate the period of rotation of the small cog. Now this will be omega equals 2 pi by t. With t being the subject of the formula, this is going to be 2 pi divided by omega. T equals 2 pi divided by 37. This t is going to become 0.1698 seconds, which becomes 0.17 seconds. And the assumption is that the angular speed is constant because we have V equals R omega. If this is constant, then V is proportional to R for the same system. Show that the distance moved by point X on the chain after one full rotation of the small cog is 0.24. So for example, there could be a point X here, and after the small cog has made a full rotation, for example like this, where will this point have moved to a new location? So if you find the circumference of this smaller cog, we can equate this to the distance moved by X. So simply put, this will be equal to 2 pi r equals 2 pi into 0.038, and this becomes 0.238 meters, which will be 0.24 meters. Use the information in B3 to determine the angle through which the cog. Now this is an interesting question. Large cog rotates during one full rotation of the small cog. So the problem lies in the fact that this one is going to make a full rotation and this one is going to make some rotation like this. And the idea of the similarity would be that whatever the circumference of this is, the small cog, which is 2 pi r, the distance traveled in this side would also be exactly the same. And it will actually qualify as the arc length, right? So what we're supposed to do here is this. So what we can do is simply find the distance ratio. So that would be 0.24 divided by into 2 pi divided by 2 pi into 0.15. So this comes out as 1.6 radians, or 1.6 radians as an angle. You can convert this into degrees as well if you multiply this with 2 pi. Okay. All right. And the idea is that this is the distance lengthwise versus the distance circular-wise. I'm multiplying this with 2 pi so that we can convert this into radians, right? Because that is theta equals s divided by r. So this is going to be as angle 1.6. Now, the next question is the chain of the bicycle in B is moved along a smaller cog fixed to the wheel. So if the cog is smaller, the radius will be smaller. The speed of the bicycle does not change, so the V is not changing. He says, explain without calculation the effect of the change angular speed of the pedals. So since the X is going to be moving a smaller distance, as if this cog is smaller in size, this one is smaller in size, this X will be a smaller distance. That's quite obvious. Now, if that is smaller, if X is smaller in the same amount of time, then the angle covered will also be smaller. If the angle covered here on the larger section is smaller this time, for the same amount of time, for example, this is omega equals to, let's say, 2 pi r divided by t, whatever this angle is, for example, right? So covering the same angular speed we have right now is here. This is going to be smaller angular speed, right? Okay. Question number 2. Question number 2, the first definition is about gravitational field line, which is they represent direction of force on a test mass. This is interesting. A test mass idea is simply requesting or simply demanding that whatever gravitational object you want to test the gravitational field of, the other mass should be on the outer side. And what will happen to this mass? It is going to get attracted. So if you place that mass here, this is going to get attracted. If you place the mass here, it will be attracted. So no matter the orientation, since it's being attracted in all directions, being attracted by the larger mass, these actually lead us towards the gravitational field lines being radial. That's what we mean by that. 90 degrees, inwards 90 degrees. You don't need to draw the 90-degree symbol. It's just for your understanding for the students coming to this question. All right. We've covered this part. So the next part is considered as Earth acting as a long solenoid magnet, which is fine. Geographic poles, which is on the axis of rotation. He says figure 2.3 is a copy of figure 2.2. Okay, fine. Without labels, but with two magnetic field lines shown, which is fine. The first part is label the magnetic poles north and south. So based on the arrows, we can say that this is south and this is north. The next question is draw field lines to represent Earth's magnetic field outside the Earth. They're going to behave like a bar magnet. Okay. So it's going to be from north to south. Obviously, I'm not very good at this, but please try to make sure that the images are mirror images of one another. This is pointing towards this side. This is going to be pointing this side. So if you notice from the south end, they're coming into the South Pole. And if you notice from the North Pole, they are moving away from the North Pole, like this. So you're pretty much done with this part too. An observer moves around the surface of the Earth. Use your answer in A2, this one, to explain why the observed gravitational field of the Earth does not vary around the surface. You see, the gravitational field lines are like this. They are radial. Since they are radial, they are uniform around all aspects of around all the surfaces. If I wanted to draw more, we can draw more, which means that the person walking around through them, if the person keeps walking like this, he's experiencing the same number of lines of gravitational field. He's experiencing the same spacing between the gravitational fields, which means that the strength of gravitational field lines, or G for that matter, is going to be constant or fairly constant. So the reasoning for that is it does not vary because the lines are perpendicular to the surface and are evenly spaced. Okay. And when we say perpendicular, it means that based on the surface, they could be moving like this, they could have moved like this, but no, they're moving like this, completely perpendicular to the surface. So whatever the person walking through them experiences is not going to change. Part 2. With reference to your answer in B2, the previous part, this one probably, yeah. He says, describe how the observed magnetic field of the Earth varies around the surface. Now, the gravitational field does not get affected, but the magnetic field does. You see, let's for example say that the person is standing here. At this point, the magnetic field will be the strongest, and they will be perpendicular to the surface. But if the person keeps moving like this, for example, they keep walking, walking, and walking, The magnetic field strength will be the weakest around the equator point because they're highly spaced. They're further away from each other. And as it starts moving away to the other pole, towards the other pole, the strength of magnetic field will start increasing. So that's what they have mentioned here. Okay, it's just a matter of observation of how you and I perceive fields. That's what we're interested in. Okay. Question number 3. Heat capacity, familiar with the definition. It's 1 kg mass, 1 Kelvin change in temperature per unit change in temperature and per unit mass. So we're familiar with that. Okay, and this is Q equals to mc delta T. Now part B gives us a bit of information. There is volume at temperature 0. Then the density is at temperature 0. The density is this at 500. And you can notice that the density is slightly higher when it's at a lower temperature because molecules and particles are closer to one another. All right. So he says calculate the mass of the block. So density is equal to mass by volume. Density will be used for the part when the temperature was same. Now, since I have two informations at 0 degrees centigrade, it's logical to use them as the information provided. So 2.7 into 10 raised to power 3 equals mass divided by volume is 3.612 into 10 raised to power minus 3. Now notice that they're giving us the values up to 4 significant figures. So my final answer should also be up to 4 significant figures. I have to be careful about this. Now once you find the mass by multiplying them together, your answer is going to be 9.752. This is 9.752. Part 2, show that the volume of the block at a temperature of 500 is this. Now, since it's a show that part, it's very likely it's going to be very easy. So now we have, again, density is equal to mass divided by volume. So the density we have is what we, for the second part, is 2.6. Right, so this is 2.62 into 10 raised to the power 3. Mass is going to remain the same because that does not change, divided by volume, new volume. This volume is going to come out as 3.722 into 10 raised to the power minus 3. So we have successfully shown this as minus 3 meter cube. The next part we have is part 3. Use information in B2 to determine the magnitude of work done on the block when its temperature is raised from 0 to 500. Now, the formula for work done is very simple. P delta V. The atmospheric pressure is mentioned in the question here. And the change in volume experienced by the object or this block is going to be this and this. Right? So, the external pressure is 1.01 into 10 raised to the power 5 into 3.722 into 10 raised to the power minus 3 minus 3.612 into 10 raised to the power minus 3. And this comes out as 11.11. Now notice that this is a 3 significant figure number. These are 4 significant figures. So my natural inclination will be towards the least number of significant figures, which is 11.1 joules. So when the box, for example, be that this cube was provided with thermal energy, it expanded slightly. And now the new dimensions are going to look like this. All right. Something to think about. Okay, explain whether the work done on the block is positive or negative. Now this is work done on the block. All right, and the block is expanding in a very simple sense. It's expanding. And the only way an object can expand or do something or do some work against the atmospheric pressure is by taking energy away from the internal energy, by spending that amount of energy that it already has. So the volume, we mentioned that the volume of the block increases as it expands against the atmospheric pressure. It is pushing back against the atmospheric pressure. It needs to apply some force on the surface, on the skin, which means it's going to require some energy. So naturally, the energy that we found in the previous part needs to have a negative sign, which means that the reason that the block expanded, even if we heated this, so whatever thermal energy we poured in, some of that thermal energy has been converted into P delta V. So naturally, since it is being taken away from the system, the energy has to be negative. Now he says use the first law of thermodynamics to determine to three significant figures a value of specific heat capacity for aluminium. Explain your reasoning, give a unit with your answer. So first we need to define what type of energy are we left with, or what energy do we have still. So he mentions that the increase in internal energy of the block is 4.38. This happened when we provided thermal energy. Now the first law states that the change in internal energy should be equal to the heating supplied and the work done. Now this value is 4.38 into 10 raised to power 6 as mentioned in the question. This is what we need because heating will eventually become equal to mc delta T. Now the simple idea is, as I mentioned earlier, we provided the thermal energy and two things happened. The first one, the energy was used as P delta V for thermal expansion. And the second thing that happened was an increase in internal energy, which becomes Q plus W. So that's the idea behind this one, right? Now this is plus into minus 11.1. We added a negative sign depicting that it took the energy away from the thermal energy store. So what we are left with, now this is a very small number, definitely. It's going to go over to the other side and become an addition symbol. But even if we add this number together, it's not going to put a significant change on this number. So this is 4.38 into 10 raised to power 6. Now, even if this doesn't make any difference to the value of this quantity, the examiner still needs to see this because he wants to make sure that you know and understand what this is. So now we use 4.38 into 10 raised to power 6 equals the mass of the block, which should remain same and does not change, is the number of atoms. C into change in temperature is 500. Now, no need to worry about the fact that the temperature is given in degree centigrade or something else. We are always interested in the change. So change in Kelvin or change in degree centigrade is always the same. C is going to come out as 898.277, which becomes 898 up to three significant figures as mentioned by the examiner, and the unit will be joules per kg degree centigrade. Next question is, without further calculation, suggest with a reason how doubling the pressure in B is likely to affect the answer in B4. You see, if we go back to this situation, if I double this pressure, this answer will be doubled. And if today it's 11 joules, even if on that day it becomes, for the sake of example, double that, which is going to be around 22.2 joules, does it still get subtracted from the, or added to the value, and does it still make a difference? No, it doesn't. So effectively speaking, for solid objects, the work done, P delta V, is generally zero, considered zero, because it doesn't matter. And that's what I've written down in the answer. Work done is negligible compared to the change in internal energy. Hence, there will be no change in the answer of specific heat capacity. We've got the same answer again. All right, now we have the equation of state in an ideal gas may be written as this, XYZ, PVA equals NBT. All right, so this is a common question, the 4.1. He says, mention what the meaning of T is as thermodynamic temperature. Don't write down temperature. Because when you write down thermodynamic temperature, it means you're talking about Kelvin. Part B, identify the constant B. And it is the universal gas, molar gas constant, which is R. Now we have the product PV is given by the equation, which is one of the derivations that you do generally. Part 1, state the meaning. Okay, so M is mass of one. This is the key word. It's mass of one molecule. And that's the beauty of this equation, because these are macroscopic properties. The pressure and the volume is for the full container, is for the full room you're sitting inside right now. And if by any chance you were able to grab onto just one molecule, be that oxygen, carbon dioxide, nitrogen, from your room and study its behavior, for example, that behavior can depict the behavior of the whole system, right? So this is a connect between these two equations, but anyways. C is mean squared speed of the molecule. Then we have used the equations A and B to derive an expression in terms of ABT for the mean kinetic energy of a molecule of the gas. Keyword. Now, the first equation they've given us is PVA equals capital NBT. The second equation that they've given us is PV equals to 1 by 3 Nm RMS speed squared. Now, since this is equal to PV, this is equal to PV, we can bring A to the other side in division to make it look like this. Then let's make both of the equations equal to each other. So this is 1 over 2 nmc squared equals nbt divided by A. It's pretty obvious that some of the letters get cancelled, n gets cancelled. We are left with, since we're talking about kinetic energy, this part remaining is kinetic energy. Yeah. This was 1 by 3. And no, this is 1 by 3. Yeah. So how do we make sure that we get half mb squared in this? So let's take to the other side. This becomes mc squared equals 3bt divided by capital A. And if by any chance, for example, we want to multiply this with 2 and divide this, multiply both sides by 1 over 2, that would be a better choice. 1 by 2, and this is also 1 by 2. When I do that, the left-hand side becomes equal to the kinetic energy, and the right-hand side becomes 3bt divided by 2a. So the expression should be 3bt divided by 2a. Part C, he says RMS speed with temperature. So whenever you get a graph like this one, either in P2, P1, or P4, you're supposed to find a mathematical equation before you draw this graph. And definitely this is going to start from origin. Why? Because RMS speed depends on temperature. And if you remember, 3 by 2 kT was equal to 1 over 2 mc squared. So the thermodynamic temperature is dependent on the speed, or RMS speed. So let's bring that out, because everything else is constant, only speed and temperature are linked. And we have c squared being proportional to t. This is on the y-axis and this is on the x-axis. Because I'm interested in the y-axis, I have to make this the subject of the formula, so the under root has to go to the other side. This becomes c being proportional to under root t. Now it's your job as a mathematics student to know the trends and behaviors of the graph. So y proportional to x is a straight line from the origin. Y proportional to x squared is like a parabolic equation, could be in any shape. For example, like this one, this one, this one. It should be a curve like that one. And the other bit is this one. This has been very recent in terms of how he's been asking this question. So what does this look like? It's obvious that increasing t increases the speed. So it's going to be a graph like this one with an increasing trend on both axes. But if you notice, which one is getting more balanced out, or which is going to get more normalized? You see, since it is being calculated as an under root, even if I put a very, very large number, the under root actually balances it out. It actually curbs its value. So based on that idea, the increase in t should be more than increase in RMS speed. If you're not convinced with this explanation, you can just simply go back online and search the graph of y proportional to under root x. We can find that relationship here. That's what we're looking at. But what does that generally look like, so we can apply this everywhere else? The graph of this is going to look something like this. Now notice that in the ending section, the temperature increase or the change is very high, but it's not translating into an increase in RMS speed. And that this behavior is actually the graph for a y relationship with under root x. But anyway, that's math, not physics. You can get by about that on your own. Question 5, simple harmonic motion, very common definition. Acceleration directly proportional to displacement, and acceleration is opposite to displacement. A block is suspended by a spring. Block oscillates vertically. Okay, fine. V is given as t, a function of time. V is in meters per second, and t is in seconds. Calculate the period of the oscillation. So if I want to find that out, we knew that we have a workaround, which was V naught cosine of omega t. So 16 is the value of omega, right? Because t is of my choice. I put the t based on where I want to observe the graph. All right, so again, back to the formula, which is omega equals to 2 pi by t. And this will be 16 equals to 2 pi divided by t. T is going to come out as 0.3926, which becomes 0.39. Determine the amplitude x naught. Now for these questions, it's always a good idea to use the voltage speed equation, which is plus minus omega. under root x naught square minus x square. Now the idea behind this is that this is actually the amplitude. This is the amplitude where the object might go when there was no restriction. So since that is the criteria for the question, this can only happen when we have the maximum speed as one of the data points. Yeah. All right. So this is going to become 16 plus minus 16 under root square root x square minus x square, right? Now, what was the velocity in this situation? The v naught, or the peak velocity, is 0.56. So here we have 0.56 equals 16. Now, since we are interested in the maximum, we put the maximum speed in, omega stays constant, so this x has to be 0, because this maximum speed only happens when the pendulum or the oscillating mass crosses from the origin or the starting point. Why? Because at that moment exactly, there is effectively no force, no restoring force responsible for bringing it back, which is why the speed is maximum in that situation. So 16 x naught will be equal to 0.035 meters. Okay, so this is 0.035. Part 3. Use your answer in B2 to determine the equation for V in terms of the displacement x of the block, where V is in meters per second and x is in meters. No problem at all. So in this case, we are just going to give them the expression, so which was V equals, this was going to be plus minus 16 with the under root as x naught square minus x squared. Now we're just going to replace the values here. So this is going to be plus minus 16 under root 0.035. A good idea to put brackets a whole square, and x squared. This is an interesting question and has been asked many times recently. Let me just clear this out. So we have the data with us, right? We have the maximum speed as 0.56. This is the V naught. We have the x naught as 0.035 meters. So we're just supposed to plot these points over here. You see, the maximum displacement actually happens away from the main position when the object is actually not moving. The fact that we can say that it is maximum displacement tells us that it is not moving. So 3.6 will be somewhere around here, probably 3, 3, 2, 3, 4, 3, 6 here, and goes the other way, 3, 6 here. Then we have 0.56, which is over here. I think if you count the boxes, is going to be here, and then it's going to be here. So the graph of this situation is going to look something like this. It's like an oval shape, and apologies for my drawing. And if you want to find the equation behind this, this is very simple. Since it's with v and x, the current situation is going to look something like this. It is again a nonlinear relationship. Question 6. Two parallel metal plates X and Y are separated by a distance this much, shown in figure 6.1. Electron is placed. He says there's vacuum between the plates. Okay, fine. Use symbol plus and minus to indicate. This causes the electron to move towards Y. So this should be positive and this should be negative. And done. Okay. The energy electric field strength between the plates, give your answer in that format. So E used to be equal to delta V, or potential difference, divided by D. The potential difference is 58,000 volts. So 58,000 divided by the distance between the plates is 0.041. 0.041. The answer to this question will be 1.41 into 10 raised to the power 6 newtons per coulomb, or newtons per coulombs. So this is 1.41 into 10 raised to the power 6. Determine the acceleration of the electron. It's not a problem because there must be some forces acting on it. So between the plates there was an electric force which can be found by QE, and there was a resultant force which can be found by MA as F. Since they're both forces, they can be equated with each other, which means that QE is equal to MA. Now he's asking about the acceleration. Let's make A the subject of the formula. This becomes A equals QE divided by M. Now, do I have these values with me for the sake of this calculation? Yes, we do. So this is elementary charge as 1.6 power minus 19. E is in the previous part, 1.41 minus 6 power 6. And whole divided by the mass of the electron, which is 9.11 into 10 raised to the power minus 31. And in this case, the acceleration comes out as 2.5 into 10 raised to the power 17 meters per second. Very, very high rate of acceleration. He says many electrons are now accelerated. Okay, fine. When the electrons hit vibrate, the absorption kinetic energy results in emission. Okay, fine. Show that the minimum wavelength of these minimum wavelength, which means frequency, is very high. Can you pass from this place or not? This is what he was trying to do. So, of these electrons is 21 picometers. Show that. So how can we show that? What we can do is use the photons formula, which is E equals to hc by lambda. Okay, and this is, what's 50? hc by lambda, and we have energy equals to QV, sorry. So I'm going to equate both of these equations, right? Because I'm interested in the wavelength, so this is going to become 6.63 into 10 raised to the minus 34 multiplied by speed of light, which is c divided by lambda, which is what we want to find out, equals QE or QV, sorry, 1.6 minus 19 into V voltage that's available, 58,000. So lambda comes out as 21 minus 12 meters, picometers. State the region. This is X-rays. You are supposed to memorize it. He says explain how the magnetic waves used to form images of eternal. Now he's asking about a medical physics question, right? So X-ray passes through the body, transmitted waves measured. Some passes through the tissue, some passes through the bone. There's a difference of absorptions by both materials, and it sets up a good contrast. You see, at different amounts, a difference in their intensities is used for the image using a powerful computer. Question 7 is about capacitors. A simple capacitor is given to you with the C and switch and R. He says initially the switch is open. The potential difference is this, which means that the capacitor has 12 volts to spend. At time t0, the switch equivalent capacitor discharges through the resistor. Okay, fine. These are attributes given to us. Shows the variation of current, charge with voltage, and current with resistance. State the relationship between VC and VR. When you close the switch, they will definitely be very, very equal to each other. There is no loss in the series configuration. Determine the capacitance C in microfarads. So we're going to go and see which figure suits well. This one suits well because we are trying to find out the capacitance. So Q equals to CV is one of the formulas, and Q is 7.2 into 10 raised to the power minus 3, and C into 12. So we can find the C here. The C comes out as 6 into 10 raised to the power minus 4 farads. You see where the 12 actually comes from is the battery. And this is that initial condition. It's not shown, but there is one. So this will be 600 into 10 raised to the power minus 6. As mentioned here by the examiner already. So you don't have to write down the 10 raised to the power minus 6. He says calculate the resistance R. So we have a very simple formula, which is V equals to IR. And according to figure 7.3, I have current and I have voltage. I can do that for them. Yeah, so voltage is 8. Current is 1 into 10 raised to the power minus 3 multiplied by R. and R is going to come out as 8,000 ohms, which is a very big resistor, and it's a very good design that at least there's someone in the circuit to protect everything. Okay. All right, and we took this value at 8. You are exactly on the dot. So we couldn't be better than this. The time constant of the circuit is tau equals to RC. Resistance is 8,000 and capacitance is also very high, which is 600 micro. This is 600 into 10 raised to the minus 6. So calculate जरूर कीजिएगा and find the answer. This is going to come out as 4.8 seconds. This is 4.8. Part C. He says, now this is a bit tricky. He says use both figures to answer your answer in part A. Explain why the variation of Q and T is exponential in nature. First, let's try to understand what the thought process is. You see, the current in the resistor is proportional to the voltage of the resistor, which is proportional to the voltage of the capacitor, which is proportional to the charge itself. Okay. Now, if, for example, we bring this here, the current in the circuit being equal to the rate of change of charge, we are already doing that when we are looking at the graph 7.2. We're already doing that. We are calculating the rate of charge, right? So this is also Q. Now this bit is confusing. He says we can conclude that Q is to IR is equal to IR. And since IR equals delta Q, delta divided by delta T, it's like this. Q is proportional to the rate of change. Now, since any quantity becomes proportional to anyone else, let's say anything, but divided by time, becomes this. Yeah, this one, this equation. Replace the variables in terms of English and then you can use them freely. So it's a maths problem, it's a maths thing, it's not physics. Why it was going to be an exponential variation with time. Question number 8. A good question in that sense. V out, V in is this. The positive will be blocked, the negative will be allowed to flow, as you can see in the circuit too. Rectification is half wave. Why? Because there's only one diode. And how about this? The resistor R has a resistance of 45 ohms. In the circuit, this is 45 ohms. Assume that there is no potential difference across the diode when it's conducting, which it generally does, but let's say that it doesn't. Determine the peak power. So peak power is equal to V peak squared divided by R. So the peak is, I think we missed a part, sorry, we missed a part here. So calculate V naught. Now for V naught, we are supposed to go back to, yeah, this is V in as 6 volts, which is RMS. If I want to find the peak, so that will be V RMS multiplied by under root 2, which is 6 multiplied by 1 under root 2, which is going to become 8.48. So this becomes 8.5. Now here we have the peak voltage, which becomes 8.5 squared divided by R is 45. The mean power comes out as 1.605 watts, which becomes 1.60. Second part is interesting. He says draw the output waveform. Now notice that since it's a half-wave rectifier, only the negative cycle will be extracted and the positive will be rejected, due to the nature of the orientation of the diode. The current, let's say that this is the power supply, this is positive, this is negative. The current tries to go this way, it doesn't allow it. Now, for example, in this case, I think it's some students. Yeah. All right, so in this case, when the current goes from the negative side, it is allowed to flow through. So the negative cycle will be completed, but the positive cycle would be left alone. So first, let's mark those points which are going to be flat or going to stay flat, not participating at all. Next, we want to figure out the peak point. So the peak will be the center. Okay, fine. And now we draw a smooth curve through them. If you notice, I've mentioned that only for these power graphs, the graph is supposed to curve like this. Other graphs can end abruptly. The graph in this syllabus does not. Use the answer in B2 to explain why the mean power in the resistor is 1 by 4. You see, the mean power is actually calculated like this because it's going to be peak divided by 2 multiplied by 1 by 2. Why am I multiplying by 1 by 2? Why am I halving the value? Right? So the reason is that we're only getting half of the power out. This is what we do for converting peak power to mean power. And this is what we've done to reduce that half cycle that we never got. Okay, so this one comes out as, I haven't probably calculated the values, but this is what it will look like. Yeah, I think I have, 0.5 naught, 5 P naught. And then he says the mean power in the resistor is 1 by 4. You see, it's already being halved. And when you take this half as well in the same time frame like this one, you definitely go below your budget and the mean power reduces. That's what I've written down here. You can pause the video and read this on your own and see what you can make of it. Use the information in B3, the previous part, determine the RMS V out, RMS value of this situation. So there are one way. So this will be P mean equals V RMS squared divided by R. So P mean, or the mean value this time around for the half-wave rectifier, will be P by 4. So the previous part, if you were able to find the power, which was 1.6 here, that power will be used here. All right, and one more thing, this has to be divided by 4, VRMS squared, and now we have VRMS as 4.242 volts. So this is going to be the RMS voltage. Question 9. He says, state what is meant by the photoelectric effect. We are familiar with the definition, so I'm not getting into that. The main issue is with the question. Now, first understand the question. The question says if there's a stage 1 where the frequency was fixed, okay, and electromagnetic radiation is coming here and the electrons are emitted to go towards X. X is connected to the negative terminal via potentiometer. Or you want to say variable resistor, that's completely fine. That means that electrons would not want to come to the X. Unless X is at 0 volts, there will always be few electrons that will never make it because plate X will be repelling them. So that's one thing to keep in mind. The second stage, or in the first stage, what he does is he keeps on increasing the current, keeps on increasing the voltage until no current is observed. And then you realize that he has completely stopped the electrons from coming in, which they were coming in earlier. Explain with the reference to photons why Vs depends on the frequency of the incident electromagnetic. Now, Vs is the threshold voltage, minimum amount of voltage required for this question. For this question, be advised, is a minimum amount of voltage required to stop the electrons from coming in. Because there are a range of electrons, they're coming from all directions, and they are going towards all directions, it's very imperative to understand that if we apply voltage to the negative plate, it can repel those charges and not accept them to begin with. So here, the way we talk about this, that it is specific and fractional and quantized, is this. So energy of photon depends on its frequency, yes. Energy of the electron depends on incident photon, yes. The higher the frequency, the higher the versus needed to stop, the higher the Vs voltage needed to stop the electrons from reaching X and showing current on the ammeter. Hence, Vs depends on the frequency of the incident photon. So there are many options, many answers. All of them are right. Use 3 quantitative. Now, this is one of the questions that has caused some trouble to some students. You see, he says three quantitative conclusions. These are quantitative. You need to show numbers. No qualitative treatment. Qualitative means that you're going to talk about this whole setup in theory. What's happening to, let's say, voltage, what's happening to current, what's happening to resistance. so on and so forth, something like this. But we are not doing that here, okay? We are looking for something that is quantitative, that is a value in terms of some calculation. You see, the first point I've already written down, the threshold frequency is 1.5 by power 15. How do we get this? This is where we pick that value from. But why here? You see, if we notice at this point, the voltage required to stop the current still stays 0, which means the electron has not been able to come out. So only after the threshold frequency or the photon has been crossed or has been received do we see some requirement of voltage to be applied so that we can stop them, right? So as we increase the frequency, high energy photons start coming in, leading to an unbalance of this equation, which is HF equals to phi plus half mv squared. Okay, all right. So the first conclusion is fine. Now, using the same information, we can find the second information, which is V equals to F lambda, which becomes 3 into 10 raised to power 8 meters per second. Frequency is 1.5 into 10 raised to power 15 into lambda. The lambda here comes out as 2.07 into 10 raised to power minus 7. It's not 7 here. Minus 7 meters. So this is second information. The third information is about the photon that is being received at that location, which is going to be E equals to HF. We are using figure, let me just go back. We're using this figure 9.3 in this case. So in figure 9.3, I have H, which is 6.63 into 10 raised to the power minus 34. Frequency is 1.5 into 10 raised to the power minus 15. This comes out as 9.94995 into 10 raised to the power minus 19 joules. If you divide this with 1.6 into 10 raised to the power minus 19, you convert this into electron volts. And that is 6.22 electron volts. So far we've made 3 points. Let's make a few more. Can we calculate the Planck's constant? Yes, we can. So for Planck's constant, what we are supposed to do is HF must be equal to the work function. Yeah. So work function or the energy supplied by the plates. Okay. All right. So the energy supplied as work function or from the work function or being demanded from the work function is very simple. So H is what we want to find out. F is 1.5 into 10 raised to the power positive 15. And phi is 6.22 into 10 raised to the power minus, it's electron volts. So this will be EV converted into 1.6 into 10 raised to the power minus 19 to convert it into joules. Now when you solve this as H, your answer comes out as 6.63 something into 10 raised to the power minus 34 joule seconds. This is also one of the options. Okay. Now let's explore option number 5. Option number 5 says the number of photons coming towards the plate at stage 1. So we can go back to figure, let's say 9.2 and see what the current is here. The current here is 20 or 2.7 into 10 raised to the power minus 3. This current represents the number of electrons. And how do we know that? Very simple. So current is 2.7 into 10 raised to the power minus 3. Q is equal to number of electrons or number of charges, and T is the time in seconds, right? So let's do that first. So 2.7 into 10 raised to the power minus 3 equals number of electrons, which is 1.6 into 10 raised to the power minus 19, divided by time T, which is going to be taken as 1 second, because we're finding everything in per unit watts. So this is minus 19, and when you take this to this side, and not this one, but we're solving for n, so this will come here. So n comes out as 1.6875 into 10 raised to the power 16, which becomes 1.7 up to true significant power 6 meters. Not meters, but number. Yeah, is number of electrons. Now this is the fifth one. Now let's go to the sixth point. The sixth point in your marking scheme, how do you find the justification for that? So it says that show that the power is 0.028. And we've seemed to find the solution for that. You see, the problem at this stage was that power is definitely energy divided by time. That's for sure. Time is 1 second, so we're not bothered about that. If we're bothered about the energy, we do have the number of photons. You might forget to put the frequency as 1.5. So this is 1.7 into power 6 into. So what is the energy? These are the number of atoms. What is the energy of a single photon emission? You might be confused by using 1.5, but this time around we're not doing that. If you read the question carefully, stage 1 had a frequency as a different frequency, 2.5 power 15. That's why the answer is different from 1.5. So here we will calculate the HC divided by lambda again for the said circuit. Let me just look at the circuit again. Yeah, we need to do that again. So this one today is 1.7 into HF, the energy brought in by the photon. So 6.63 into 10 raised to the power minus 34 into 2.5 into 10 raised to the power 15 hertz. All right. Now pressure P is equal to, this one gives you 0.18 watts to it. So I've explained all the 6 situations given the marking here. I hope you understand them too. Question number 10, he says, state the meaning of context, the term spontaneous. Yes, it doesn't, it happens on its own. It does not depend on the external environmental conditions. These are the initial conditions. These are given to you. He says, complete the table for the expressions. So half-life, for half-life of X, it's very simple. This is 4A, check for 2 ways. This is going to happen at 2t, half 2 to 1. This happens here. So for the sake of half-lives, we are absolutely bang on for X. So this is 2t. The life of Y, half-life of Y. So if this is 1, for example, this is 1, which is 40, approximately. Is it 1? Yeah, it is. So it should be started from 0.5. So 0.5 gives me 3t. And I'm sure if you go further, much further down, half of this will bring you 60. Okay? So this is, the half-life is 3t. Now the decay constant, we have a general equation for decay constant, which is either lambda equals to ln2 by t half, or t half is equal to ln2 by lambda. These two are interchangeable. So the decay constant, lambda, is equal to ln2 by half-life, this one. So I'm writing that down, ln2 divided by the half-life. Half-life is 2t. This is also ln3 by 3t. Yeah. It says the initial number of nuclei. We want to find the number of nuclei. So activity is equal to lambda n, okay? And if I want to find the initial activity for the first one, which is this x, so that would be simply 4a as the initial activity. Current initial activity could be anything, and since they're interchangeable, okay? And that would become n naught, number of particles, e raised to power negative, no, not e. We can simply do it by this method, as using this equation, because we have the decay constant with us, right? So this is going to be ln of 2 divided by 2t. and this is A equals N naught 4A, and this was A, this is A N naught, and this was ln3 by, sorry, this is also ln2 by 3t. Yeah. Now, since we want to find the initial number, let's make N naught the subject of the formula. That is the main goal. So if I simplify this, this is going to come out as 8AT divided by ln of 2. This is going to come out as 3AT divided by ln of 2. Next, we have determine in terms of capital T the time for which the two samples will have equal activities. Now, for the sake of equal activities, it's going to be a very hectic mathematical procedure, so please bear with me. So they're going to be equal. Let's do this for x, and then do this for y. So x says A equals 4 times A naught, e raised to the power negative ln 2 divided by 2t, and then t itself. Ratio A equals A naught e raised to the power negative ln 2 divided by 3t into 1 over, sorry, not 1 over, but t exactly, into t. We can see that clearly that at least A naught and A naught are getting cancelled, right? And what we're left with is this equation, is A naught e raised to the power negative ln 2 divided by 2t, capital T, into t equals 4A naught. Which one has the 4 bar? This one. 4A naught into negative ln 2 divided by 3t into t, right? It wants you to find the value of capital T. So can we be smart about this? Can we pick out some trick or rule here? Right, so this cancels, A naught cancels. What I'm left with is just numbers. So if we apply the natural log here, natural log, this will come out something like this. So ln of 4 plus ln of, rather t ln of 2 divided by 3t equals ln 2 by 2t. And it's all because of this. From this point onwards, you have to do the algebra. You want to make the capital T the subject of the formula. Take your time. I've done this on another piece of paper. It does require half a page to be solved. You can find a different trick for this. So this will become ln of 4 plus t ln of 2 divided by 3t equals ln of 2 divided by 2t. The next step is taking the LCM here. So this becomes 3t ln of 4 plus t ln of 2 equals whole divided by 3t. This is ln of 2 divided by 2t. Then the next stage is to bring 3t to the side. So this becomes 3t ln of 4 plus t ln of 2 equals 3t ln of 2 divided by 2. Since this is also variable, this is also variable t, we can take this to the side and subtract them collectively to get this. So today this becomes 3t ln of 4 equals 1 over 2t ln of 2. And since we want this to be the subject of the formula, this goes to the side. This becomes 6t multiplied by ln of 4 divided by ln of 2 equals capital T. This is what we wanted to find. Yeah? All right. Just a moment. Yeah, this is absolutely fine. You can check the algebra again one more time if it confuses you. Now, solve this on the calculator. You will find that this comes out as 2. And then 6t multiplied by 2 becomes 12t. Last part. This is a repeated part. He says, what's the difference? So there is a disconnect between what is being measured, what is being received, and what do we have on the inside of the radioactive sample. So for example, if this is the sample on the inside, what do we know what's happening on the inside? We don't. We can only guess when we're standing on the outside using a GM tube. Whatever radiation gets into the GM tube is what could be our answer. So that's what is mentioned here. Why is there a disconnect between the two things? Radiation is emitted in all directions, not just towards the sensor or GM tube. That's why. Some radiation absorbed by the air while going to the sensor, some radiation not detected by the detector even though it reaches it, which could be a sign of faulty detector. Okay? All right, that is all for May, June 2025, paper 42. I'll see you in the next one.